In today's building and construction industry, the choice of different glazing materials continues to expand, suiting several different applications. With so many choices, architects need to understand the unique value each material brings to a certain application. Also, strict attention needs to be given to model building code classifications for a particular application. One important area within the model building codes revolves around flammability properties. Traditional flammability test methods, such as ASTM D635, measuring horizontal burn rate, ASTM D2843, measuring smoke density, ASTM D1929, measuring ignition temperature, and ASTM E84, measuring flame spread and smoke development, rank materials based on performance in small to medium-scale fire tests. These tests do not necessarily use configurations or exposure conditions represented in end-use applications. However, these tests serve to evaluate materials on a relative basis and are used as screening tests for flammability properties. Tests simulating real-world situations, exposing materials as close to end-use situations as possible, should be given higher consideration when specifying a material for an application. Polycarbonate multi-wall sheet and fiber-reinforced plastic sandwich panels are both classified as CC1, Class A interior finish glazing materials, from the small to medium-scale fire tests we just outlined. You will see, however, a very different reaction from these materials when tested in a room-scale environment. This large-scale test is meant to more closely simulate real circumstances, and in this controlled environment, allows us to evaluate their behavior under actual full-scale fire conditions. The materials being tested are two common light-transmitting plastics used in a variety of vertical and overhead glazing applications, such as glass replacement windows, skylights, curtain walls, solariums, barrel vaults, and other covered walkways. All applications would normally be found in schools and non-residential construction environments. The material on the left is polycarbonate multi-wall sheet, which is a plastic extruded material from polycarbonate resin. The thickness of the material is 10 millimeters, which is about 2/5 of an inch, and dimensions of the sheets were as follows: 2 upper wall panels made up of one 2-foot by 6-foot section and one 2-foot by 10-foot section, 2 overhead ceiling panels made up of 4-foot by 8-foot sections, and 2 corner wall panels made up of 2-foot by 8-foot sections. The material was placed in a common metal frame which typically holds polycarbonate multi-wall sheet for vertical and overhead glazing applications. The material on the right is a fiber-reinforced plastic, commonly known as FRP sandwich panel, which is manufactured from polyester resin. The overall thickness of the structure is 2 3/4 inch, made up of common sandwich-type construction on a typical metal frame. The inside face consisted of a nominal 0.045-inch fiberglass reinforced polymer, and the outside face consisted of a nominal 0.070-inch fiberglass reinforced polymer. Additional glass fibers, acting as an insulating material, filled the space between the panels. The FRP sandwich panel dimensions were as follows: 2 upper wall panels made up of one 2-foot by 6-foot section and one 2-foot by 10-foot section, 2 overhead ceiling panels made up of 4-foot by 8-foot sections, and 2 corner wall panels made up of 2-foot by 8-foot sections. The FRP sandwich panel was made of typical construction found in vertical and overhead glazing applications. References for setting up this room-scale flame test included ASTM E603, Standard Guide for Room Fire Experiments, NFPA 265, Fire Tests for Evaluating Room Fire Growth Contribution of Textile Wall Coverings, and UBC Standard 26-3. These are guides and standards that address methods of conducting room-scale fire testing to full-scale fire conditions for material evaluation. Dimensions of the wooden-framed building were 8 feet high by 8 feet wide by 12 feet deep. The doorway opening was 30 inches by 80 inches and was located in the center of the far wall from the fire source. The test area consisted of 2 wall corner sections totaling 32 square feet, intersecting at the corner opposite the doorway. 2 upper wall specimens covering a total area of 32 square feet, with 2 edges adjoining the intersecting wall test sections. Additionally, 64 square feet of overhead specimens join the 2 ceiling specimens for a total exposed area of 128 square feet. Both materials were framed, mounted, and installed in typical fashion for a plastic glazing material. The balance of the room was covered with drywall. The fuel source and ignition method is outlined in UBC Standard 26-3. The fuel source consisted of a wood crib constructed of 1.5-inch square white Douglas fir. This fir was cut to 15-inch lengths. The 10-tier crib assembly required a total of 50 sticks. The crib rested on bricks that had been cut in half, each one supporting a corner of the crib not less than 3 inches above the floor. Starter material was 1 pound of shredded fluffed wood excelsior distributed around the bricks, with the excelsior extending from the wall and covering approximately a 21-inch by 21-inch area. The location of the fuel source was placed in the corner of the room opposite the doorway. To start the test, all but one corner of the excelsior is soaked with 4 ounces of ethyl alcohol. A match is then placed in the dry corner of the excelsior to initiate burning. The criteria for evaluating the performance of a glazing material for both vertical and overhead applications within a room can be based both on what occurs within the room and what occurs outside of the room. One key factor affecting building occupants outside of the room where a fire occurs is total heat and energy released from the involved area. This heat and energy distributes smoke and hot gases throughout the building. When a room reaches flashover, the possibility of escape for the occupants in an adjacent area is reduced substantially. Flashover is typically defined when any of the following 2 conditions have been attained. Heat flux at the floor reaches 25 kilowatts per square meter. Average upper air temperature exceeds 1200 degrees Fahrenheit. Flames exit the doorway. And lastly, spontaneous ignition of a paper target on floor occurs. For this video, a visual of flames exiting the doorway, as well as spontaneous combustion of a paper target in the middle of the floor, will be the determinants of flashover. Observe the smoke buildup and the time to flashover in the room. As the fire develops, observe the materials and watch for the following: melting behavior and the material's ability to aid in fueling and spreading the flames. Notice if the venting of smoke and hot gases is occurring, or is there a buildup within the room. Look for extent of spreading flames and signs of flashover. About 1.5 minutes into the test, heavy black smoke bellows from the FRP sandwich panels. There is no venting of this smoke, which causes accumulation buildup in the room, behavior that is a life safety negative. Notice that the smoke in the polycarbonate glazed room is low. This is due to smoke venting through the melted polycarbonate, behavior that can be a positive life safety characteristic. The burning FRP sandwich panels sustain flames which now reach the ceiling, behavior that is also a life safety negative. Because no venting of smoke and heat occurs, extreme feedback effect on the crib and surrounding ignition sources consume the room, fueling the flames. As the polycarbonate multi-wall sheet bows away from the fire once it reaches its melting temperature, notice that it does not sustain its own combustion and does not spread flame, a positive life safety behavior. Just over 2.5 minutes elapse, and now temperatures reach flashover in the FRP sandwich panel glazed room, igniting the crumpled paper while sending flame spread out of the doorway. Remember, this is a material that tested well for ASTM E84 measuring flame spread and smoke development. Heat and smoke continue to vent through the melted polycarbonate, keeping the room from reaching flashover. Notice the crumpled paper in the center of the room never ignites. The polycarbonate multi-wall sheet does not sustain its own combustion. Therefore, the fire remains localized to the burning crib. Notice the continued smoke buildup from the FRP glazed room and the flame spread to the backside of the building. The fire continues to remain localized to the crib in the polycarbonate glazed room. Feedback effects continue to drive the flame height within the FRP sandwich panel room, leading to possible continued flame spread. Because the polycarbonate multi-wall sheets melted away from the flame source, venting occurs and minimum feedback affect the crib, keeping the flames to lower heights. Notice how the FRP sandwich panels continue to support its own combustion, demonstrated by the involved panels seen in the rear of the building. This could serve as a source for continued flame spread throughout a building. The polycarbonate multi-wall glazed room continues to vent the hot gases and smoke and does not support its own combustion. Therefore, flame spread is reduced significantly. As both cribs eventually collapse and the fire inside of the room diminishes, the polycarbonate multi-wall glazed room did not support its own combustion and therefore is left with no afterburning. The FRP sandwich panel glazed room supported its own combustion and therefore continues to be involved at the rear of the building with continued smoke build and potential flame spread. When evaluating different light-transmitting plastic glazing materials for vertical and overhead applications, several considerations need to be taken into account. Fire safety is one consideration that cannot be compromised nor ignored. Full-scale fire tests, like the one you just saw, provide additional information on how a material will react within a full-scale fire exposure. Small-scale tests, on the other hand, may not accurately simulate real-life behavior of a wall covering or overhead glazing material. Flashover effects, for instance, are not seen, and these small-scale tests do not show behaviors that can be fully evaluated for their life safety implication. What you have seen in this video are two Class A CC1 interior finish-rated materials showing demonstrably different fire performances under actual fire conditions. Life safety concerns are many for burning FRP sandwich panels. There is no venting of heavy black smoke that develops. There's flame propagation and a high feedback effect on the crib and surrounding ignition sources. Flashover does occur. Polycarbonate multi-wall sheet burning did not bring the room to flashover. There was smoke, but venting through the melted sheet minimized buildup in the room and its feedback effects to the crib. The material did not sustain its own combustion and did not spread flame.